And today we are going to discuss about the bridge domain, bridge virtual interface, VPLS. It's related to configuration and basic troubleshooting steps. So let's start. So first we will discuss about the bridge domain. So exactly what is the bridge domain? It's a nothing but bridge domain is nothing but the same broadcast domain. So if we same broadcast domain under the bridge domain, it will have same IP subnet. So if we see here, suppose this is having this one IP address and this one is having 1.1.1.3/24, and suppose he is having 1.1.1.4/24. So you can see here all these are part of same broadcast domain. So if any if a part of same broadcast domain, if any bump traffic hits from here, any broadcast unknown unicast and multicast traffic hits here, it will pass on the all interfaces. And if any known unicast hits here, so it will see that from where he has learned the MAC address. Based on that one, it will forward on that port. So router will just act as a switch here, and it will forward the MAC address according to that one. So here is the bridge domain definition. So next we will see the sample configuration for the bridge domain. So here we can see that we have defined this interface as L2 transport. We are defining here encapsulation is dot one Q2S2, means VLAN is 2, and we are removing that top one VLAN. So here it is a rewrite index tag pop on symmetry. So it will be almost similar configuration for other three interfaces. And let us see the bridge domain configuration. So here it is under L2 VPN. Here it is bridge group configuration customer 1. Bridge domain name is engineering, and under that bridge domain we have called all these three interface, this one. So all these three interfaces become part of the same bridge domain, and they will pass the traffic each other. Miss it simply a router will just act as a transparent device. So here a bridge group will simply hold all this configuration. Like if any X company is there, so it will act as bridge group, and under that company we can say that HR department is there, then again IT department is there, then again purchase department is there. So all this will act as a separate bridge domain, and each and every department will have their own MAC address table. They will not interfere with other broadcast domains. So here we will see some basic troubleshooting steps or some command output for this bridge domain. So we can see here show L2 VPN bridge domain group. This is bridge group, this is bridge domain name. Here we can see that we have configured 3 attachment circuit and all are showing up. So here this particular detail about those particular attachment circuit and all are showing up. Here we don't have any virtual forwarding instance configured, so it will be 0. So for if customer is complaining that he is not able to pass any traffic for this particular bridge domain, so you can verify using this particular command show L2 VPN bridge domain group. This is bridge domain group number customer 1, BD name, this is bridge domain name, and you can verify this counter, how many counter it has received and sent. Suppose if any customer edge device is there, and this is PE devices, so you can ping from here and verify how many counters it has received and how many counter it has sent back. So based on that one you can troubleshoot it like that. So we can see that counters for all interface under this bridge domain. So we can check the MAC address table as well, as we discussed already. So each BD will have their own MAC address table associated. Bridge group will not have MAC address table, but it will be associated with each bridge domain as we discussed earlier. So that MAC address table we can verify using show L2 VPN forwarding bridge domain. This is bridge group : bridge domain name, MAC address, and the location, that line card location we need to mention. and we can see here we are learning the MAC address on each and every interfaces. Next one is L2 VPN resynchronize forwarding MAC address table. So generally when frame hits the routers, so it will learn that MAC address table and store in the hardware table. So and when you execute this particular command, it will fetch that output from software table. So when you enter this command, it will try to software table will try to sync with hardware table, and it may, if table is very large, it may take 15 seconds to completely synchronize with the hardware table. So after 15 seconds, if whatever information software table has, it will display in this command. So if table is very large, so sometimes you may miss some output here. So in that case, if you want to synchronize completely hardware table with the software table, then you can execute this command, layer 2 you can resynchronize forwarding MAC address table location and that line card name. So it will get completely synchronized, and you will get the complete output here. Next is BVI, Bridge Virtual Interface. So what is exactly the Bridge Virtual Interface? So if this device wants to communicate with each other, they can easily communicate because they are part of same broadcast domain, or we can say bridge domain. But what if they want to communicate outside world beyond these devices? So in that case, we need to configure the Bridge Virtual Interface. It's a bridge virtual interface is virtual interface within the router, just act as like a normal routed interface. It does not support a bridging itself, but it acts as a gateway for the correspondence bridge domain to routed interface. Only one BVI can be configured under this bridge domain, and same BVI you cannot use under the other bridge domain. BVI is associated with a single bridge domain and represent like a link between bridging and routing interface. Means this is a bridge domain and this is the routed world. So you can say that BVI is a link between that bridge domain and routed world. So a packet from host on a bridge interface goes to BVI if destination MAC address matches to the BVI MAC address. Suppose if I am trying to go outside, and if MAC address matches with the BVI, then only I'll route the packet, else I'll bridge the packet with the other interfaces. And when the packet hits from outside world towards this host, then BVI will send that packet to the routing engine before sending them out to the routed interface. And one more problem is that BVI don't understand the VLAN tag. So if you are any VLAN tag, or if any traffic is hitting here with the VLAN tag, you need to remove that complete stack and you need to send it to BVI. That's the reason this command is very useful here. Rewrite ingress tag. So you need to remove all the complete VLAN stack and you need to send it to BVI, because BVI don't understand the VLAN tag. So while troubleshooting, if traffic is, if you are not able to pass your traffic, so you need to pay attention on this command if you are using the BVI. So here is the sample configuration for the BVI. So interface configuration are almost similar like earlier bridge domain configuration. So here we can see this is the bridge domain configuration, same like earlier, and under that bridge domain we have called the routed interface BVI 20. So we can see here it's BVI 20, and here it's a BVI 20 configuration. So we have defined here IP address as 1.1.1/24. So on this router, on this customer devices, I can define as a default gateway as 1.1.1.1, or I can configure as a default route as mentioned here. So here I am defining the default gateway 1.1.1 and or else default route as pointing towards the 1.1.1. So means the traffic which is not matched with these remaining devices, it will go via BVI to the remaining world. So next portion we will discuss about the multi-point services, that is VPLS, virtual private LAN services. So here is just schematic diagram for this VPLS. So here we can see that VPLS network requires creation of bridge domain. So here we can see that this is the bridge domain on PE1, this is the bridge domain on PE2, this is the bridge domain on PE4, this is the bridge domain on PE3. So each devices have their own bridge domain. So each device will be associated with each bridge domain, and we can see here virtual forwarding interface configured on each devices, which will point towards the remote devices, and it will form the pseudo wires between each device, each PE devices. It will become fully meshed devices. So we can see that virtual forwarding interface binds the bridge domain of one PE with the other, so that it will become the complete one broadcast domain or bridge domain for the customer network, so that traffic can be transparently go via this pseudo wire. So customer CE1 will feel directly attached with the CE5. So we can see the configuration here. So here is the interface configured as L2 transport, here is the VLAN, and here is the rewrite ingress tag 1 pop symmetry. The same almost similar configuration on other attachment circuit for other Ps, same here. So here now we will see the VPLS configuration. So here we can see that under L2 VPN bridge group VPLS dash test, bridge domain is L2 VPN, and I have called that attachment circuit or EFP under that bridge domain. So here we can see that this is the complete bridge domain configuration. Now we will configure the VFI. So this is the attachment circuit, or we can say that bridge domain, and next we will configure the VFI. So under VFI L2 VPN VFI. So under VFI I have defined the neighbors and pseudo wire. This pseudo wire number should be same on all the PEs which are part of same broadcast domain. So pseudo wire will be formed between those two PEs. So we can say that VFI and BD will VFI and BD will join together, and it will form the complete broadcast domain for customer. On other PE configuration will be almost similar. Means here it is bridge domain, here it is VPI part, here it is bridge domain, here it is VFI, and we are joining that bridge domain using that VFI. Next we will see some basic troubleshooting commands. So we can check show L2 VPN bridge domain group VPLS test brief. So here we can see that this is a bridge group and bridge domain name. So under that one we can see it is showing status up. So we have configured one attachment circuit under that one, and it is showing up. So we have configured two pseudo wires and both are showing up. So we can say that pseudo wires are running fine. So VPLS form between other Ps. Next we can check the show L2 VPN bridge domain group, that bridge domain name, and here we can figure out that this is bridge group, this is bridge domain name, and we can see the status is up, running fine. So here we can see the attachment circuit, here is the attachment circuit, state is up, and here we can see the VFI. So both VFI it's showing and both are up. So you can verify this command for control plane verification. Next we can see the MAC address table for this particular VPLS. Show L2 VPN forwarding bridge domain. This is bridge group and this is bridge domain, MAC address table, and that line card location. So here we can see that this particular MAC address I am learning on this attachment circuit, and this particular MAC address I am learning over the pseudo wire. And again, if there is a synchronization issue, you can run this command L2 VPN synchronize forwarding MAC address table location and that line card location. Next, you can verify the show MPLS forwarding table as well, because one labels assignment will be there under that show MPLS forwarding. So you can verify that for particular pseudo wire, and also you can verify the traffic counters using these byte counters. So next is we can verify the data plane counters. So here show L2 VPN forwarding bridge domain, bridge group, then bridge domain name, detail, location, and that line card location. So here you can see that on particular attachment I have received the 11 and sent it, I have received the one packet, and I have sent the 11 packet out of that interface. So you can see here if I am pinging from the customer edge towards this particular PE devices. So here we can verify how many packets I have received and how many packet I have sent back towards the PE. The same counter we can verify for the attachment circuit as well. So suppose if this is the pseudo wire formed with the other PE router, so we can verify those packets I am receiving, I am sending it towards on the pseudo wire or not. And again, the packet I am receiving back on the pseudo wires are not from the remote PE. On the remote PE, again you can verify those same counters for troubleshooting purpose. Here we can see that packet receive and send counter for this remote PE. Again, if any particular customer is complaining about the reachability issue, so in that case we can verify using either using layer 2 ACL or layer 3 ACL. So we can apply this layer 3 ACL on attachment circuit. So we can apply on inbound and outbound both direction to verify that packet. So these are customer edge IP address. So once we see if customer traffic is going through, once we hit the counter, we can see the hit here 100 or 200 like that. So we can verify both on ingress and egress direction. Same it is for the layer 2 ACL. So these are customer edge MAC address, and I have applied this ACL under the attachment circuit on both ingress and egress direction. So we can see here show access list, Ethernet service, layer 2 VPN MAC ACL, hardware, ingress, and location. On egress direction we can verify on egress, and we can see some counters hitting here or not. So this will be very useful for if any single customer is complaining about the traffic. Auto discovery and signaling. So when you add a new VPLS PE to the network, the configure the PE in order to have pseudo wire to all existing PE in each of its local bridge domain. All existing PE must be reconfigured in order to have pseudo wire to new PEs, because PE must be full limit. Suppose if I have these many PEs configured here, so these will have pseudo wire, a full mesh pseudo wire with each other. So if I am adding a new devices, so I need to configure here. Again, I need to configure on all 4 devices. Again, if I am adding any other devices, again I need to configure here. I need to configure again on all devices. So this manual configuration changes add operational cost and increase the chances of network misconfiguration. So solution for this is auto discovery using the BGP. So VPLS auto discovery eliminates needs to manual provision of VPLS neighbor. Or VPLS auto discovery automatically detects when PE added or removed into the VPLS domain. So if you have any VPLS domain, so if you have any RR configure here, so you just need to configure the BGP with between. So if you add any one devices, you just need to configure the BGP, and then signaling will automatically form based on the BGP. So here we can see the sample configuration for BGP signaling. So this is the bridge domain configuration for this particular attachment circuit, and this is the VPLS part. So under VPLS we have defined VFI. So this is VPN ID, auto discovery will be BGP, and RD is auto, route target we have defined. So signaling protocol is BGP, so we can use either BGP or LDP, and this is VEID. So on the remote devices you should match, VPN ID should be same and route target should be same, but VEID should be different on each peer router to form the pseudo wire. So under BGP we need to define the address family L2 VPLS dash VPWS. So under that neighbor I am configuring that particular address family. Same configuration will go on the remote PE. Once everything works fine, then pseudo wire will come based on the BGP, because here signaling protocol we are using as a BGP. We can verify using the show. So there are two primary functions for VPLS control plane. One is auto discovery, that will happen using BGP, and second is setup and tear down of pseudo wire that constitute VPLS. So for the pseudo wire we can use either BGP signaling or LDP signaling. So both of these functions are accomplished using the simple BGP update advertisement. BGP needs to distribute network layer reachability information for VPLS bridge domain with P as a BGP next hop and appropriate VEID. Additionally, VPLS is associated with one or more BGP route target and that are distributed along with NLRI. So VPLS address family and sub address family is also distributed under that BGP update advertisement. So here we can see that show BGP L2 VPLS command. So here we can see that we are learning the bridge domain information on each P routers here with labels information. Next is using the LDP signaling. So for the LDP signaling, configuration remains almost same except for these two configuration. Signaling protocol should be LDP and VPLS ID should be configured under that for that LDP signaling. Rest configuration is almost similar. A P router advertises an identifier through BGP for VPLS in the case of LDP signaling. This identifier is unique within the VPLS instance and act as a VPLS ID. The identifier enables the P router receiving the BGP advertisement to identify VPLS associated with the advertisement and import it to correct VPLS instance. In this manner, for each VPLS, a P router learns the other P router that are member of VPLS. The LDP protocol is used to configure pseudo wire to all other P routers. The fake 129 is used for signaling. This information is carried by fake 129 include VPLS ID, target attachment individual identifier, source attachment individual identifier. So for LDP we are using fake 129 and for BGP we are using fake 128. Next is hierarchical VPN. Next is hierarchical VPN. To avoid the looping frame inside the MPLS network, some rules are there like split horizon rules. Suppose if I am receiving any frame on this particular pseudo wire, I will not be able to forward it on other pseudo wire. So this is called a split horizon rule. So due to that split horizon rule, spanning tree protocol is not required in the IS under the core. To manage that one, so we need to have full mesh of pseudo wire connectivity between each and its devices. So if P devices grows, so it's become very difficult to configure all these devices and manage and it may become scalability issue. So if we configured each VPLS device, suppose n into n minus 1 divided by 2 pseudo wire will form. Suppose if we have 5 VPLS devices, so 5 into 4 divided by 2 is equal to 10 pseudo wires will be there. But suppose if from 5 if we increase it to 10, so it will become 10 multiplied by 9 divided by 2 is equal to 45. So you can see the drastically increase in the number of pseudo wire. So it's become very difficult to manage all these devices, and it's become signaling overhead, and real detriment to large scale deployment is the packet replication requirement for each provision pseudo wire on the P router. So to avoid this one, we can use the hierarchical structure. So here we can see that this is attachment circuit, this is user PE, this is network facing PE. So here we have configured the attachment circuit, and the interface between user PE and NPE will act as a cross connect, means it will act as a point to point connection. So here we can see that on user PE we have L2VPN cross connect group customer 1, and we have called that attachment circuit, and here is the neighbor ID which is network facing PE. So it is become as a point to point for between user PE and network PE. On the network PE, this will become part of bridge domain. So this will this IP address belongs to user PE, and here under VFI we have configured the remote PE devices IP address with their pseudo wire IDs. So we can see that we are forming the pseudo wire with remote PEs. So same on the remote side. So we can see that the user PE devices has attachment circuit. So this is attachment circuit, and user PE device transports CE traffic over MPLS point to point. As we discussed, this becomes point to point pseudo wire to the network provided device. The NPE is a core VPLS PE. So this is the core VPLS PE which will have full mesh with the remaining devices, and it will form the multi-point pseudo wire between each devices. The UPE is not a part of mesh. On the other hand, ENPE. So the ENPE is considered the access pseudo wire as an attachment circuit. So we can see that it will consider this as an attachment circuit, and forward traffic from the access pseudo wire to the core device that are part of VPLS port. So if traffic comes here, it will simply route it over the VPLS. And the core pseudo wire between NPs are configured under VFI in order to ensure the split horizon. So suppose if I am getting any traffic from here, I will not be able to forward to this VPLS pseudo wire, because those are part of same split horizon group, because those are configured under the same VFI instance. And access P from user P's are not configured under VFI, so they do not belong to same split horizon group as VFI. So traffic can be forwarded from access pseudo wire to VFI and vice versa. Means we can traffic from here to any other pseudo wires.